Hello, I am Algebra Master, and I am starting a new series on YouTube. This series is called Blindly Mathematical. Blindly Mathematical is a series about recreational mathematics meant to be accessible to people with visual impairments and or with little or no sight, if you want to be more specific. There are plenty of good YouTube channels out there, such as Numberphile, Mythologer, 3 Blue, 1 Brown, and Presh Talwalker's Mind Your Decisions, but unfortunately most of those are very visual, and that's fine if you're a visual thinker and if you can see well, but if you can't, those channels aren't the most accessible. So I decided to try and reach out to an untapped audience, an audience of people with visual impairments, people who, if they could, might want to learn recreational mathematics, but ordinarily wouldn't be given the opportunity to mess around with some of the tougher problems math has to offer. And this is unfair to people with a visual disability because there's no reason why they can't be just as mathematically gifted as some sighted people. After all, mathematical sight is not the same as eyesight. Mathematical sight is just, do you have the ability to solve tough math problems? So that's the purpose of Blindly Mathematical. This is all about, can you solve tough math problems, even without your sight? So I'll present a math channel in that format. In my first episode of Season 1, I will talk about the Collatz conjecture. The Collatz conjecture is a conjecture made by Lothar Collatz in 1937 about a little bit of a number game. This number game is played with these two formulas and whole numbers. So to set the stage for the number game, imagine starting with any whole number. The whole number should be 1 or greater. And your job is to figure out first, which formula should I plug it into? And then what your result will be when you plug it in. So if your number is even, that means if it's divisible by 2, then divide it by 2. And that will give you your output number. After that, then we'll see where to go from there. Now, for the first, now if it's not even, if your number is odd, then multiply it by 3, and then add 1. So let's take an example. If you start with 3, 3 is odd, multiply by 3, giving you 9, add 1, that's 10. Or if you started with 5, that'd be 3 times 5 is 15, add 1, that's 16. Or if you started with 7, 3 times 7 is 21, add 1, that's 22. So or if you started with an even number, such as 10, 10 divided by 2 is 5, 12 divided by 2 is 6, 14 divided by 2 is 7, and so on. So play this game again and again. So start with a number. We'll call this your seed number. Plug it into whichever formula it goes with, depending upon if it's even or odd. Then take your result and plug it back into whichever formula that should go with. So say you start with 10, take 10, divide it by 2, that gives you 5. Now take that number, plug it back in, only this time, since it's odd, plug it into the formula, 3 times that number plus 1, so 3 times 5 plus 1 is 16. So, that process you just did there is called reiterating. Every time you take the answer you got from a function or a formula and plug it back into another formula or even that same formula, that's a new iteration. So each time you do that, it's a new iteration, and the process of doing that again and again is called reiteration. So Lothar Collatz said that if you continuously apply this process again and again, or you continue to reiterate, that eventually you will always reach one in a finite number of steps. So going back to that, we look at the numbers that are generated, you plug in 10, you get 5, you plug in 5, you get 16, you plug in 16, you get 8, you plug in 8, you get 4, you plug in 4, you get 2, you plug in 2, you get 1. So that one reaches 1, but that could work for pretty much any other number you could try. In fact, mathematicians have tried all numbers from 1 all the way up to numbers as big as 10 to the 14th power. That's a 1 with 14 zeros after it. And even bigger. They have tried numbers so big that you would need computers to mess around with them. Like, you can't even you can't even conceptually figure out how to calculate numbers so big by hand. It just takes way too long. And that's a bit of the problem. You know, there's an infinite number of numbers. You can't possibly check them all. And Lothar Collatz is proposing, wait, so this works for all whole numbers I could pick. Like, no matter what whole number I pick over 1, it will always reach 1. I think it would help to start with to try another example. So say we, start with 14. 14, plug that in, you get 7. Take 7, plug that in, you get 22. Take 22, plug that in, you get 11. Take 11, plug that in, you get 34. Then you get 17. The next iteration is 52, 26, 13. And each new number you get is a new iteration. So 13, 40, 20, 10, 5, 16, 8, 4, 2, 1. And interestingly enough, this contains the other sequence I mentioned, the one starting with 5, or the one starting with 10. Some sequences contain each other like this. And this is an interesting feature that people have noticed. Another interesting thing you can notice is that, well, anytime you plug in an odd number, it always leads to an even, because 3 times an odd is an odd. Add 1 to an odd, you get an even. So that's nice. Another nice thing is that, if what Lothar Collatz says is true, all sequences will be finite in length. So they contain a finite number of numbers, which means you can sort them from least to greatest. Every sequence has a largest number, and every chain of iterations has a smallest number. You can think of them as their maximum and minimum. So far, this problem has not been solved. Some people think the problem's unsolvable. Some people are jokingly offering money for the solution of the problem, like Paul Erdos jokingly offered $500 for it, and said that mathematics is not ready for this problem yet. So maybe you can prove him wrong. Try this problem out for yourself, remember the formulas, and this concludes episode 1 of Blindly Mathematical.